Imagine discovering a fundamental law of the universe, one that connects the very fabric of reality in an elegant mathematical principle. Now imagine being denied professorships, having to lecture under a male colleague's name, and receiving no salary for your work. This was the reality for Emmy Noether, perhaps the most important mathematician you've never heard of. When Albert Einstein called someone a creative mathematical genius, you'd think they'd be celebrated throughout history. Yet Emmy Noether's name remains largely unknown outside academic circles, even though her theorem forms the backbone of modern physics. While Einstein and Newton became household names, Noether's revolutionary work remained in the shadows, another brilliant woman erased from the popular story of scientific progress. Today, we're uncovering the extraordinary life of Emmy Noether, the mathematician who changed physics forever while battling the pervasive sexism of early 20th century academia. This is the story of how one woman's elegant mathematics revealed the deep connection between symmetry and conservation laws, a principle so profound that it continues to guide our understanding of the universe today. Welcome to the Pondering Posters series, Forgotten Women Who Changed History. Today, we're exploring the life and revolutionary contributions of Emmy Noether, a mathematical genius whose theorem fundamentally transformed our understanding of physics. Born in 1882 in Erlangen, Germany, Emmy Noether would go on to develop one of the most important mathematical principles in physics, despite facing systemic discrimination that denied her the positions, pay, and recognition her male counterparts received. Her theorem, elegantly connecting symmetry and conservation laws, isn't just some abstract concept. It explains why the direction of your morning commute doesn't affect how much energy your car uses, why a physicist in Germany gets the same experimental results as one in Japan, and even underpins our understanding of particle physics and quantum mechanics. Yet, while her male colleagues achieved fame and recognition, Noether's name faded into relative obscurity. Today, we're changing that narrative, giving Emmy Noether the recognition she deserves as one of history's most important scientific minds. Emmy Noether was born on March 23, 1882, in the Bavarian city of Erlangen to a middle-class Jewish family. Her father, Max Noether, was a mathematics professor at the University of Erlangen, creating an intellectually stimulating environment for young Emmy. But the path wasn't clear for a mathematically gifted girl in late 19th century Germany. As a child, Emmy wasn't considered exceptional. She learned domestic skills like cooking and cleaning, as was expected of young women. She initially planned to become a language teacher, one of the few acceptable careers for educated women at the time. After passing the required examinations to teach French and English at girls' schools, something shifted. Mathematics began to call her. Perhaps influenced by her father's profession or driven by her own innate curiosity, Emmy decided to pursue higher education in mathematics, an almost unheard-of aspiration for women at the time. Here's where her first major battle against institutional sexism began. The University of Erlangen, where her father taught, didn't accept female students. The university regulations stated clearly, "Academic regulations do not foresee the admission of women students. The Senate is not in a position to make an exception." Undeterred, Emmy sought permission to audit classes, to sit in without receiving official credit. Even this required special permission from each professor. From 1900 to 1902, she attended classes as an auditor, absorbing complex mathematical concepts while denied the official status of student. In 1903, policies finally changed, and at age 21, Emmy was properly admitted to the University of Göttingen, another prestigious German institution. But after just one semester, she returned to Erlangen when it finally opened its doors to female students. In 1907, at age 25, Emmy Noether accomplished something remarkable. She completed her dissertation on invariant theory and received her doctorate in mathematics, summa cum laude. Yet even with this exceptional achievement, the professional doors that would have automatically opened for a man remained firmly closed to her. For the next 7 years, Emmy worked at the Mathematical Institute of Erlangen without position or salary, occasionally substituting for her father when he was ill. She published papers and began to build a reputation among mathematicians who recognized her talent, but institutional recognition remained elusive. Her brilliance was evident, her talent undeniable, yet the academic world wasn't ready to give a woman her rightful place. This pattern would continue throughout her career. Exceptional work met with exceptional barriers. In 1915, a pivotal moment arrived in Emmy Noether's career. Two mathematical giants, David Hilbert and Felix Klein, invited her to join the prestigious Mathematical Center at the University of Göttingen. They recognized her exceptional talent and wanted her help with a specific problem related to Einstein's newly developed general theory of relativity. Einstein had just completed his revolutionary work, but there were still mathematical puzzles to solve. The conservation of energy in this new curved spacetime framework wasn't behaving as expected. This wasn't a trivial problem. It struck at the heart of whether Einstein's theory could be reconciled with one of physics' most fundamental principles. While working on this challenge, Emmy Noether discovered something profound, something that would change physics forever. She found a deep, elegant connection between symmetries in nature and conservation laws. This became known as Noether's theorem. Let me explain this revolutionary insight in simpler terms. Noether proved that for every symmetry in nature, there must be a corresponding conservation law, and vice versa. If a physical system behaves the same regardless of position, then momentum must be conserved. If it behaves the same regardless of time, energy must be conserved. This was more than just an elegant mathematical proof. It was a revelation about the fundamental structure of reality. Einstein himself recognized its significance, writing, "Fräulein Noether was the most significant creative mathematical genius thus far produced since the higher education of women began." Yet despite this groundbreaking work and endorsements from figures like Einstein and Hilbert, Noether still faced institutional barriers. When Hilbert proposed her for a faculty position, the opposition was fierce. One faculty member famously objected, "What will our soldiers think when they return to the university and find that they are required to learn at the feet of a woman?" Hilbert, frustrated by this blatant sexism, responded with his famous retort, "I do not see that the sex of the candidate is an argument against her admission as a privat docent. After all, we are a university, not a bathhouse." Despite Hilbert's advocacy, the university refused to grant Noether a proper position. For years, she taught under Hilbert's name, with her courses listed as Mathematical Physics Seminar by Professor Hilbert, with the assistance of Dr. Noether. She received no salary from the university for her teaching. Let that sink in. One of the most brilliant mathematical minds of the century taught without formal recognition and without pay, simply because she was a woman. Yet during this difficult period, Noether's mathematical output was extraordinary. Beyond her famous theorem, she made revolutionary contributions to abstract algebra, transforming it from a collection of disconnected results into a powerful, unified framework. She essentially created the field of abstract algebra as we know it today, developing concepts like ring theory that are now fundamental to pure mathematics. Her mathematical style was distinctive. While many mathematicians sought concrete solutions to specific problems, Noether thought in terms of general structures and abstract patterns. This approach, looking for the deeper patterns behind mathematical phenomena, proved incredibly fruitful, opening entire new fields of mathematics. To truly appreciate Emmy Noether's genius, let's explore her famous theorem more deeply. Noether's theorem might sound abstract, but it's actually something we can understand through everyday examples. Imagine you're conducting an experiment in your lab. If the laws of physics work the same way regardless of where you perform your experiment, whether in New York, Tokyo, or on the moon, adjusting for gravity, of course, that's a symmetry of space. Noether's theorem tells us this symmetry directly leads to the conservation of momentum. Similarly, if your experiment gives the same results whether you perform it today, tomorrow, or next year, that's a symmetry of time. Noether showed this symmetry directly causes energy conservation. Even the principle that physics doesn't care which direction you're facing, rotational symmetry, leads directly to the conservation of angular momentum, explaining why ice skaters spin faster when they pull in their arms. Before Noether, these conservation laws seemed like separate, unrelated principles that just happened to be true about our universe. Her genius was in showing they all stem from a single, elegant mathematical principle connecting symmetry and conservation. The implications were enormous. In one mathematical stroke, she had unified and explained the conservation laws that form the bedrock of physics. Her theorem becomes particularly crucial in quantum field theory, particle physics, and our attempts to understand the fundamental forces of nature. To appreciate just how profound this insight was, consider physicist Frank Wilczek's perspective. It is increasingly clear that Noether's theorem is the single most important tool for understanding the deep implications of symmetry in physics. Think about that. A woman who couldn't even get properly hired at a university developed what would become the single most important tool in theoretical physics. And the theorem wasn't just mathematically elegant, it was practical. When physicists encountered a new symmetry in nature, Noether's theorem told them there must be a corresponding conservation law. When they found a conservation law, it pointed to an underlying symmetry. This predictive power makes her theorem an invaluable guide in developing new physical theories. The great physicist, Eugene Wigner, noted that if you understand Noether's theorem deeply, you understand much of the basis for modern physics. Yet how many people outside of physics and mathematics have ever heard her name? Despite her groundbreaking work, official recognition came slowly for Emmy Noether. It wasn't until 1922, 15 years after her doctorate and 7 years after her famous theorem, that she was finally granted the title of unofficial associate professor at Göttingen. Even then, the position came without tenure and with minimal pay. The mathematician Norbert Wiener described her situation. Miss Noether was a great mathematician, the greatest, I firmly believe, that her sex has ever produced, and one of the top 4 or 5 mathematicians of her time. However, she was never given a regular position worthy of her abilities. Despite these obstacles, Emmy built a community of devoted students and colleagues. She became known for her generosity with ideas and her collaborative approach to mathematics. Her students called themselves Noether's boys, even the women, and she fostered a vibrant, creative mathematical environment. Her lectures were renowned for their depth and insight, if not for their organization. One colleague described her teaching style. Completely unaware of any pedagogical devices and tricks, she would, with her eyes seemingly closed, deliver a lecture as a pure outflow of her thought at the moment, as if she were thinking aloud. She often taught while walking rapidly around the room, thinking out loud and developing ideas on the spot. Her mind worked so quickly that students sometimes struggled to keep up, but those who could follow her reasoning witnessed mathematics being created in real time. By the late 1920s, Emmy Noether had finally begun to receive some of the recognition she deserved. She was invited to speak at the International Congress of Mathematicians, a significant honor. Mathematicians from around the world recognized her brilliance, and she began to be cited as one of the leading algebraists of her time. But just as her career was reaching new heights, historical forces intervened. The rise of Nazism in Germany would soon upend her life completely. In January 1933, Adolf Hitler came to power in Germany. Within months, the Nazi government passed the Law for the Restoration of the Professional Civil Service, which removed Jews from teaching positions. Despite her significant contributions and international reputation, Emmy Noether was among the first professors dismissed from the University of Göttingen. After over 40 years in her homeland and finally achieving some recognition, she was forced into exile at age 51. With the help of Einstein and other colleagues, Noether secured a temporary position at Bryn Mawr College, a women's college in Pennsylvania. It was there, for the first time in her career, that she experienced something approaching appropriate recognition and working conditions. At Bryn Mawr, Noether continued her research and teaching. She also lectured weekly at the Institute for Advanced Study in Princeton, where Einstein had also found refuge. She embraced her new life in America with characteristic optimism and energy. Her colleague and biographer Herman Weyl later wrote, "Her courage, her frankness, her unconcern about her own fate, her conciliatory spirit, were, in the midst of all the hatred and meanness, despair and sorrow surrounding us, a moral lesson." This new chapter, however, would be tragically brief. In April 1935, after only 18 months in the United States, Emmy Noether underwent surgery for an ovarian cyst. Complications developed, and on April 14, 1935, at the age of 53, she died. Einstein wrote a heartfelt tribute in the New York Times. In the judgment of the most competent living mathematicians, Fräulein Noether was the most significant creative mathematical genius thus far produced since the higher education of women began. At a memorial service, her colleague Herman Weyl said, "Emmy Noether's significance for algebra cannot be read entirely from her own papers. She had great stimulating power, and many of her suggestions took final shape only in the works of her pupils and co-workers." This last observation points to another aspect of Noether's legacy that's often overlooked. Her influence extended far beyond her published works. Her ideas, freely shared with colleagues and students, permeated 20th century mathematics and physics, often without proper attribution. In the decades following her death, Emmy Noether's work has only grown in importance. Her theorem is now recognized as one of the most profound principles in mathematical physics, underpinning our understanding of everything from particle physics to string theory. Mathematicians recognize her as the founder of modern abstract algebra. Physicists rely on her theorem daily, yet ask the average person to name famous scientists, and Noether rarely makes the list. There are signs this is changing. In recent years, there have been more concentrated efforts to recognize Noether's contributions and use her story to inspire young women in mathematics and science. Mathematicians and physicists honor her with Noetherian rings, Noetherian modules, and Noetherian groups, mathematical structures she pioneered. The Association for Women in Mathematics established the Emmy Noether Lectures to recognize women who have made fundamental contributions to mathematics. In 2012, a Google Doodle commemorated her 130th birthday, introducing her to millions who had never heard her name. In 2016, the star HD 33564, located approximately 68 light-years from Earth in the constellation Camelopardalis, was named Emmy Noether in her honor, a fitting tribute to someone whose work illuminated the fundamental symmetries of the universe. But perhaps the most meaningful tribute comes from how central her work remains to contemporary science. Every time a physicist uses symmetry principles to predict new particles or understand fundamental forces, they're building on Noether's foundation. When mathematicians work with abstract algebraic structures, they're extending her vision. When we marvel at how the laws of physics display elegant symmetries across space and time, we're seeing the world through the lens Emmy Noether provided. What makes Noether's story particularly poignant is imagining what more she might have accomplished with proper support and recognition. How many other brilliant women throughout history have had their potential contributions diminished or erased by systemic barriers? Emmy Noether's story fits into a broader pattern of women whose scientific and mathematical contributions have been marginalized or forgotten. Consider Rosalind Franklin, whose X-ray crystallography was crucial to discovering DNA's structure, yet Watson and Crick received the Nobel Prize while her contribution was downplayed. Or Lise Meitner, who co-discovered nuclear fission but was excluded from the Nobel Prize awarded to her male colleague Otto Hahn. Going further back, there's Marie-Sophie Germain, who had to use a male pseudonym to pursue mathematics in early 19th century France. Ada Lovelace, now recognized as the first computer programmer, was long overshadowed by Charles Babbage. And Hypatia of Alexandria, the brilliant 4th century mathematician and philosopher who was murdered by a mob, with much of her work subsequently lost. This pattern continues into modern times. Jocelyn Bell Burnell discovered pulsars as a graduate student, but her male supervisor received the Nobel Prize. Katherine Johnson, Dorothy Vaughan, and Mary Jackson's critical mathematical work at NASA remained largely unknown until the book and film Hidden Figures brought their stories to light more than 50 years later. What all these women share with Emmy Noether is not just exceptional brilliance, but the experience of working against institutional barriers and having their contributions minimized, attributed to male colleagues, or forgotten entirely. The science historian Margaret Rossiter coined the term Matilda effect to describe this systematic under-recognition of women's contributions to science, named after the suffragist Matilda Joslyn Gage, who first identified the pattern. Emmy Noether's case is particularly striking because the magnitude of her contribution is so vast, and because even with endorsements from Einstein and other prominent figures, she still struggled for basic professional recognition during her lifetime. Today, Noether's theorem remains as relevant as ever. It's not a historical curiosity, it's an active, vital principle guiding cutting-edge physics. When physicists at the Large Hadron Collider confirmed the existence of the Higgs boson in 2012, they were confirming a particle whose existence was predicted through symmetry principles, the very connection between symmetry and conservation that Noether established. String theory, currently one of physics' most ambitious attempts to unify all fundamental forces, relies heavily on symmetry principles that trace back to Noether's work. Quantum field theory, which underlies our understanding of elementary particles, is founded on symmetry principles that Noether's theorem helps us understand and apply. Even our everyday understanding of conservation laws, the principles that energy can't be created or destroyed, that momentum is conserved in collisions, all these fundamental ideas are unified and explained by Noether's elegant mathematical framework. Beyond physics, Noether's algebraic innovations pervade modern mathematics. Concepts she pioneered, like rings, fields, ideals, and modules, are now standard tools across multiple branches of mathematics and theoretical computer science. Computer scientists working on cryptography, the mathematics that keeps our digital communications secure, use algebraic structures developed from Noether's foundational work. Engineers designing control systems rely on mathematical principles that build upon her contributions. Perhaps, most importantly, Noether's approach to mathematics, looking for abstract patterns and general structures rather than solving specific problems, has become the dominant paradigm in modern mathematics. She didn't just solve problems, she transformed how we think about them. Emmy Noether's story is one of extraordinary brilliance overcoming extraordinary barriers. Despite being denied positions, pay, and recognition that her male colleagues received automatically, she revolutionized both mathematics and physics. Her theorem connecting symmetry and conservation laws ranks among the most profound insights in the history of science. When we look at the elegant mathematical symmetries that govern our universe, from the conservation of energy to the behavior of fundamental particles, we're seeing the world through the framework Emmy Noether created. Her abstract algebraic structures underpin multiple branches of modern mathematics. Yet for too long, her name remained in the shadows, while her male colleagues became household names. Her struggle for basic professional recognition reflects the broader pattern of women's contributions being minimized or erased throughout scientific history. By reclaiming and celebrating Noether's legacy, we not only give credit where it's long overdue, but also inspire future generations of mathematicians and scientists from all backgrounds. The next time someone mentions Einstein's brilliance or Newton's laws, perhaps we can also speak of Noether's theorem, ensuring that this mathematical giant finally receives the widespread recognition she deserves. As we continue this series on forgotten women who changed history, Emmy Noether stands as a powerful reminder that genius knows no gender, and that the search for truth and beauty in mathematics transcends the social constraints of any era. The universe operates according to deep symmetries that reveal its fundamental conservation laws. Emmy Noether showed us this elegant connection, transforming our understanding of reality itself. In doing so, she wrote her name not just in the history books, but in the very equations that describe our universe. The images in this video were created using artificial intelligence technology. They are artistic representations intended to illustrate the narration and do not necessarily depict real people, places, or events with complete accuracy. These images should be viewed as interpretative visualizations rather than factual documentation. Thank you for watching.